Hello, ladies and gentlemen. I am Kali Rajamanthri, who is currently working as a geotechnical engineer attached to Central Expressway project in Sri Lanka. So today I will discuss about some of my findings of my master's thesis, and which is titled Stability Assessment of a Bioengineer Slope in Western Thailand. So I conducted this thesis under the guidance of Associate Professor Jotisankasa. And first of all, let's see the content for the today's presentation. It mainly inclusive of introduction to the background, study area and sample collection. And the second topic is the establishment of the surface and subsoil properties as well as the vegetation profile. So under the results and discussion, I will discuss about the two-dimensional seepage analysis using finite element method. And last topics are conclusion and references. So under the background, as we know that rain-induced shallow slope instabilities are a severe geohazard, especially in tropical climatic regions. So in order to overcome these problems, or in order to mitigate these problems, we can use various kind of methods, but among the practitioners, use of nature-based solutions are quite popular because of the low cost, aesthetic value and sustainability. So actually vegetation can be used in order to prevent the erosion as well. So the temporal and spatial variation of the vegetation property is also a vital factor when we select the appropriate plant types, because it will alter the mechanical and hydrological properties of the slope as well. So while considering the various vegetation properties, root biomass and plant age are considered as one of the important factors which affects on the hydraulic properties of the unsaturated soil zone. And this slide shows the study area that I used, and it named as Itong 1, which is located in Tompapum National Park in Kanchanaburi province, Thailand. So actually this area suffered from a mass movement and erosion in 2016. So they tried to rebuild the road embankments using geosynthetic reinforced soil together with the vetiver vegetation. So after some times of the completion of this rectification method, we collected the soil samples and we consider the plant age as 623 days. And this is how we collect the soil samples. Actually, this figure 4 shows the schematic diagram how we collect the soil samples, and this is how we collect the soil samples. And table 1 summarizes the how we collect the soil sample location. And in this case, actually, we collect the soil samples from under the root zone and 20 centimeter away from the root zone in upslope direction and 20 centimeter away from the root zone in downslope direction. And it names as UA, UR and UV for the upper layer sample. And same is applied for the lower layer samples as well. So in order to establish the surface and subsoil properties, we have considered the ground survey and UAV photogrammetry in order to find out the critical cross section, and figure 5 shows the idealized cross sections that we use for the analysis. And in order to derive the subsoil properties, we use the results that we got from the in situ Kunsel tab test results, and based on that we divided the soil layers into 3 different layers and the vegetation layers as well. So this slide shows the establishment of the vegetation profile. So in this case, we hypothesized 4 different cases by considering various vegetation locations. So actually we consider these 4 different cases in order to find the most suitable stabilization technique together with the limitation of the budget. So in order to assign the properties of the vegetation, we assign the root length based on the past literature, and other properties were assigned based on the site conditions. And this slide shows the results and discussion. So in this case, actually I will discuss the results and discussion under the 2 main topics. For the first topic is the two-dimensional seepage analysis using finite element method. So in this case, I will discuss the input functions that I use for my analysis. And under the second topic, I will discuss the slope stability and seepage analysis under the 2 case studies. And first of all, let's see the input functions that I use for my analysis. So for the first function is the soil water retention curve function. So in order to obtain the soil water retention curve, I have used KO tensiometers for a suction range of 0 to 100 kilopascal. So the figure 7 shows the soil water retention curves for the upper layer sample, and figure 8 shows the soil water retention curves for the lower layer sample. And the table 4 summarizes all the curve fitting parameters that I used using band generation method. And the next slide shows the saturated permeability values that I obtained from the conventional testing method. So prior to do this test, we have to soak the soil sample for like 7 to 10 days, and we have to obtain the degree of saturation which is greater than 95%. So according to the results, we can see that the samples which are obtained from the root zone has a very higher saturated permeability compared to the soil layer samples. And when we compare the soil layer samples, and it clearly shows that the topsoil has the quite lower saturated permeability. And in order to obtain the permeability functions, actually we have derived the permeability functions using soil water retention curves using this equation. So in this case, saturated permeability was assigned based on the laboratory test results. And figure 11 shows all the predicted permeability functions that are obtained from this equation. And in order to assign the boundary condition for the seepage analysis, first of all, I did conduct a test seepage analysis for a steady state and transient state analysis. For the steady state analysis, I assigned the groundwater table under the soil 2 by giving the pressure head equals to 0. And for the transient state analysis, I gave a rainfall of 86.4 mm per day based on the Jotisankasa et al. 2014 research. And this slide shows the derivation of the subsoil properties. As I mentioned earlier, the shear strength properties were assigned based on the in situ Kasetsart test results. As shown in this table, the soil parameters were assigned based on these in situ Kasetsart test results, and the shear strength for values for the vegetation properties for the vetiver root zones were assigned based on the past literature. And this figure 12 shows the geometry for the slope, idealized slope cross section together with the vegetation and without vegetation. Under the slope stability analysis, I will discuss about the assessment of the impact of the spatial distribution of the vegetation on the stability of the slope. So according to the obtained results, it clearly shows that when the slope is in the bare slope condition, it shows a very low factor of safety value of 1.36. And the vegetation grows on the entire ground surface, it shows a higher factor of safety of 2.06. So according to the test results, actually it clearly shows that the slope has the minimum positive impact from the vegetation when the vetiver plants are covering only the crest part of the area, only on the case 2, which has a factor of safety value of 1.74. And both of other cases have the highest factor of safety, and it has a higher variation of the factor of safety as well. So when we compare the case B case, actually in this case we consider the 4-day infiltration event, which has a total rainfall of 345.6 millimeter, and actually the variation of the water pressure regime also considered. So in this case, in order to compare these values, we selected 3 different locations: top, middle and lower cases. So in this case, variation of the water pressures for the top region, it clearly shows that the highest negative water pressure was given for the entire slope was grown on vegetation, and the marginal increase in water pressure was observed when the slope is when the 2/3 of the area was covered with the vegetation. Actually, beyond the 3 meter depth, there is no significant variation in the water pressure. So when we compare the water pressure variation in the middle region of the slope, it clearly shows that the highest negative water pressure was given for a case 2 case, actually when the 1/3 of the slope is covered with vegetation, and the highest water pressure was observed when the slope with more vegetation. Actually this can be because of the presence of the vegetation, and it increased the water pressure. So when we compare the variation of the water pressure regime for the lower region, it clearly shows that the highest negative water pressure was obtained for a case 4, actually when the entire slope is grows with vegetation. Actually it clearly shows that when the slope is with the 2/3 of the vegetation, the highest water pressure was recorded, and this can be because of the higher permeability of the root zone, and the amount of entering the water into the slope is also higher. So based on these water pressure profiles, we assess the slope stability. So according to those results, actually case 3 and case 4 has the factor of safety value of 1.65 and 1.72. So when we compare the variation of the factor of safety compared to the bare slope, actually the highest variation of the factor of safety is given for the case 4. Actually the increase in this root cohesion due to the root is more influential in the stability of the slope during a rainfall event. So finally, let's see the conclusion for this presentation. Actually, according to these results, it clearly shows that the spatial distribution is one of the important factor, and the increment in this soil permeability is jeopardized by the increment of the soil root reinforcement. Actually, further studies are required in order to assess the variation of the hydraulic conductivity of the soil with the various plant types. And the vetiver is grown on 2/3 of the slope or on the entire slope surface. The influence on the vegetation of the slope is considered as a significant factor, and we can use this in order to as a guidance for a bioengineer practice. And these are some of the references that I use for my this study. And for lastly, I would like to acknowledge my main advisor, Associate Professor Jotisankasa from Kasetsart University, and the financial support provided by the Department of the Civil Engineering and all the staff from the Geotechnical Division, Greenground Solutions, and finally the Department of Rural Roads. And thank you very much for giving your valuable time for hearing this presentation.